Yeah, welcome. So this is for AVL deletion. I'm not going to share the full code. I'll be sharing the partial code. But what do you call? This will be the assignment. This will be the assignment number 4. Okay. See, it is the normal AVL code which we have discussed, but I have just customized the code little bit by introducing some more functions. Okay. So whatever I did, I'll show you. This node definition is same, there is no change in that. Okay, and these are the pointers and the stack. With respect to push and pop, there is no change, it's same as it is. Okay, and this is the function, the same which we used with AVL to get the height of a particular node, and this is the function for identifying the balance factor of a node. There is no change. Okay, and this is the function to create an AVL tree, right? Okay, here also there is no change, it's the same code. We are asking the user to enter the number of nodes in the tree. We are creating a memory space for the root node, get the value, the key for the root node. The key is assigned to key, its left child is pointing to null, right is pointing to null. So any new node, its height will be set as 1. Then using a for loop, we are getting the other key values and it is sent to the insert function. After inserting every key, we are calling the inorder function and we are displaying it. Okay. So this is the inorder function which is used to traverse the binary search tree in an inorder style and to display it. And here is a function minimum, but I don't think I'm using this function, which is used to find the minimum of a given subtree, minimum key of the given subtree. And this is used to find whether the search function is used to find whether a particular node is there or not in the tree or not. Okay, and this max is used to get the maximum of 2 values. We want this max for updating the height. Okay, because in update height we use this max function. Okay, and rotate right, there is no change in the code of rotate right, it is ditto same. Okay, nothing changed here, it is totally untouched. There is no change in the code of rotate left, it is also untouched. Okay, and this is the code for update height for a particular node. Okay, so we check whether the node is not null. If it is not null, then the height is updated as max of height of parent arrow left child. This is height is a user defined function, it will give the height of this node, parent's left child. Similarly, when you call height with parent arrow right child, it will give that height. Okay, and previously I have shown you the max function code which will return the maximum of 2 numbers. So it will give the maximum of these 2 numbers and that will be added by 1. Okay, and then we pop the next node. Like that we keep updating the height until we reach the root node. Okay, fine. This is check and rotate. This is the function for rotating. Previously this is a part of insert code, but now I moved it into a separate function. But other than that, the code is same, only it was brought into a separate function. This part is entirely same. This function takes 2 arguments. What are they? One is a pointer called closest, the other one is a pointer called parent or the parent of closest. Okay, rest of the thing, all these codes are, it is very similar, there is no change at all. Okay, yeah, this function I'm not going to show you. This is delete in order successor. Okay, so if you are going to delete a node and that node contains a and if that node contains a right child, then we are going to delete its, then that node should be replaced with its in order successor. Okay, then we should delete the in order successor node, provided if it is a leaf node. If it is not a leaf node, again you should find the in order successor of that node. Okay, this process will continue until you reach the leaf node. Okay, and then you delete the leaf node. So this is the code for that. Okay, this I'm not going to show you. So this is a crucial code. Okay, this function you should write. Fine, not going to show you. And in order predecessor is similarly that way. Okay, and this is update branching factor. This is the code to update the branch factor. Previously this code is also part of insert, but now I have moved it into a separate function called update branch factor for a given node. Okay, for a given node. So for that particular node, it will check not only for that node, I mean it will check the branching, it will update the branching factor for all the nodes starting from the root node. Okay, right, and then it will keep checking. But in the, why this S1, you may ask? It is used to find the branching factor of all the nodes which are in the path of S1. It is used to update the branching factor of all the nodes which are in the path of S1. Okay, starting from the root. Starting from the root, we are going to update the branching factor of all the nodes which are in the path of S1. Okay, whenever the branching factor becomes less than -1 or greater than 1, then we mark that in the pointer closest, and the parent of closest will be stored in PAR. Okay, right. Actually, this code is also very similar. Okay, as that of, only thing is it is moved from insert into a separate function. Okay. Finally, when we come out of this while loop, you will have closest. You will have closest will be having the it will be pointing to the node which is whose update, whose what do you call, whichever the node whose branch factor is either less than -1 or greater than 1. Okay, if no such nodes were found, then closest will be null. In that case, we say that insertion or deletion has not created any imbalance. Otherwise, there is a imbalance. Then we call this check and rotate function, which I have shown already. For that, we are passing closest and parent, which will rotate the tree and it will ensure that it is balanced. Okay, and this is the code for insert, which it is same as that of previously. One change here I have did. See, in insert, we are going to insert the node with the key S1. So we set traverse equal to root. While traverse not equal to null, we check whether S1 is equal to traverse arrow key. Then we say that if it is found, then we say that the node with the key already exists and we come out, because you cannot have two nodes with the same key. Otherwise, we check whether S1 is less than traverse arrow key. Previously here it was prev is equal to traverse. Prev is equal to traverse. That code now it is updated as push of traverse. I am pushing that into stack. Similarly, previously here it is prev is equal to traverse. That also now I am changing into push. Okay, because this looks more professional. Okay, right. And then this is the new node. So this new node should be added to the parent of new node should be added to the at the right point. So how to get the right point? By performing a pop, we will get what is the prev. Okay, so prev is equal to pop, because whatever the node which you have pushed last, that is what we want. Because finally when it comes out of the loop, traverse will be null. Okay, before reaching null, traverse was pointing to which node? That will be the parent of this node. Okay, parent of new node, right? Okay, new node's height is set as 1. Its left pointer and right child were null. Okay, then this new node should become parents either left child or right child. That depends on the value of the new node. If new node's value S1 is less than the value or the key of previous, then it will go as a left child. Otherwise, it will come as a right child. Okay. Now, after inserting the new node, we have to update the we have to update the height of all the other nodes. Okay. So we call the function update height, which will update the height of all the nodes starting from the new node till the root node. Okay, in that path, not all, in that path. New node's parent, its parent, like that up to root, it will update the height. So then we call the update BF function, which will check the branching factor for all the nodes which are in the path of the new node. New node is S1. Okay. If there is any issue with the branching factor, that is, if there is any imbalance, then it will rotate accordingly, right? So this is the code for insert. Now coming to the code for delete. So delete also takes the key of the node which is to be deleted, right? Okay. And there are some pointers. Traverse is initially pointing to root, previous is pointing to null. Here what I am doing is, while traverse not equal to null, If S1 is equal to traverse arrow key, then we break. Otherwise, if S1 is less than traverse arrow key, then we set previous equal to traverse, traverse equal to traverse arrow left child. Else, previous equal to traverse and traverse equal to traverse arrow right child. And also we are pushing previous into the stack. Okay. Otherwise, you can also directly push. Okay. Otherwise, you can also directly instead of this also we can write push of previous. That way also we can do. Okay, fine. But anyway, we are pushing the recent parent into the stack. Okay, fine. Okay. So after coming out, if traverse is null, after coming out, if so, no such node exists to delete. Yeah, after coming out, if traverse is null, then it means that there is no node, that node doesn't exist. Okay, because when there is a match, it should come out. Okay, when there is a match, it should come out. So when there is a match, if it comes out, then traverse will not be null. Okay, if traverse is not null, then that is the node to be deleted. Okay, then we have to check whether that node has any child or not. Okay, so first we are checking whether that node has a right child or not. If it is having a right child, then we will replace that node with its in-order successor, and then we will delete the in-order successor if that is a leaf node. That will be done by this function, delete underscore in-order successor. Okay, else we check whether that node is having a left child or not. If it is having a left child, then we will delete its in-order predecessor. That will be done by this function, delete in-order predecessor. Okay, else if these two conditions were not satisfied, then it means that that is a leaf node. Okay, right? So if it is a leaf node, you can delete directly, but sometimes what will happen, that leaf node may be a root node. So that is the only node in the tree, so that is the root and the leaf. So that will happen when, how can we identify whether it is a root or not? If previous equal to null, then it means that it is a, if previous is equal to null, then it means that it is also a root node. Okay, so we take that, right? And then if previous equal to null, then we are deleting the root node and we say the tree is empty. Otherwise, if previous is not null, then we check the node that you want to delete. If that node is the left child of previous, then we make previous left child to null. Okay, otherwise it means that it is a right child, then we make previous right child to null, because traverse is the one we want to delete. Okay, and then we free up traverse, that is, that memory space is freed. Okay, suppose if previous is equal to null, if previous is not equal to null, then it means that we have to update the height of the previous node. So previous arrow height is equal to max of height of previous left child comma right child plus 1. Okay, and then we take the parent of previous by popping. Okay, we get the parent of previous by performing a pop. So when you get the parent of previous, what will happen, that height also will be updated. Okay, its height also will be updated, right? Okay, and similarly we keep updating the height of all the top nodes by calling the appropriate parent. Okay, right? So these things we do if previous is not equal to null. Suppose if previous is equal to null, then we set root is equal to null, because if previous equal to null means then the tree is empty, right? So this is the code. Okay, fine. Let me show you the output. Compiling, executing. So let us take this particular tree. This one. Okay, So if you see this tree, it has 1 2 3 4 5 6 7 8 nodes. Okay, so the number of nodes are 8. Root node is 13. Next 10, 15, 5, 11, 16, 4, 8. Okay. Do you want to insert one more? Yes. 3. Okay. After inserting 3, there is an imbalance, then it is rotated. Okay. You can see here 13 is minus 1 because they are taking right tree minus left tree. Height of right minus left, that they are taking as branching factor. We are doing as height of left minus right. So 13 height is 1. Okay. And here you can see 4 height is minus 1. In our case 4 height is 4 branching factor is 1. 15 here it is 0, but actually 15 is 1. You can see this diagram, there is no change. This is something, I think it is a typo error. It should be 1 because the left children is 0, right height is 1. Okay, right? So it is 1 minus, the height of the right subtree is 1. They are taking right subtree minus left subtree. So it is 1 minus 0 is 1. In our case, left subtree minus right subtree. So 0 minus 1 is minus 1. So that for 15 we are getting minus 1. Okay, fine. Now let us do deletion. Delete some nodes, yes. Say we will delete 3. After deleting 3, this is the state. Okay. Say then we will delete 5. This is after deleting 5. Okay. So now we have 7 nodes. Okay, then let us see delete 15. This is after deleting 15. Okay. 1, 2, 3, 4, 5, 6 nodes are there. So we have deleted 3 nodes already. Okay. Right. So then we will delete 10. So this is after deleting 10. Okay. So next we shall delete 11. This is after deleting 11. Okay. Next we shall delete 13. This is after deleting 13. Okay. Next we shall delete 16. This is after deleting 16. Okay. Next, now we have only 2 nodes. So you can see one node is at level 1, another one is at level 2. So 4 is the root node. Let me delete 4. Okay, so there is only one node. Let me delete 8. It is telling the tree is empty node. Okay, so we cannot delete anymore. So I'll give 0. Right? So this is what about deletion. So you are expected to implement this code. Okay. Right? And the deadline will be Sunday. Okay. Thank you.